Let's have a look at some more set operations. The next operation we'll have a look at is set difference. So let's quickly look at the definition. The set difference of two sets A and B, written as A difference B, is the set that contains elements which are in A and which are not in B. To read this out using set builder notation, we would have the following. A difference B equals the set of all x such that x is an element of A and x is not an element of B. So what this is saying is, we take two sets and we can form a difference between them. The first set that we consider is on the left-hand side of the difference operator, and the second set we consider is on the right-hand side of the difference operator. Taking the set on the left-hand side, in this case the A, we want to examine A, and if A has any elements that are also in B, we want to remove those elements, and the resultant set will be the difference. We'll have a look at an example shortly. The next idea that's quite important, and this is related to the intersection operation that we've just seen, is the idea of a disjoint pair of sets. So quickly have a look at the definition again here. So two sets, A and B, are said to be disjoint if they have no common elements. So that is, if their intersection is the null set. So really what we're saying here is that two sets are disjoint if they don't have any elements in common. The next set operation we need to consider is the complement operation. And the complement operation comes into effect when we're considering a universal set. So if we're given a set A with elements from some universal set, and recall the universal set is going to be the set that we're concerned with for a given problem, of all of the elements that we're concerned with. The complement of A, written A prime is the small dash at the top of the A, is the set that contains those elements of the universal set which are not in A. So that is, A prime, the complement of A, is the set, the universal set, less the elements in set A. Okay, so we're using the difference operator here to find the complement. So A complement is the set, whatever the universal set is, less those elements that are in the set A. Again, we'll have a look at an example of this shortly. Let's move on to the final operator we're going to consider, which is called symmetric difference. Let me just go through the definition first, and then we'll have an explanation of exactly what this is trying to mean. So if two sets, A and B, are given, we define their symmetric difference as the set of all elements that belong to A or to B, but not to both A and B. And we denote the symmetric difference of A and B by A with a triangle symbol for the operator for symmetric difference, and then B. So again, if we want to specify this in set builder notation, we would say A symmetric difference B is the set of all x such that x is an element of A and x is not an element of B, or x is an element of B and x is not an element of A. So if we think about this a bit more, there's a couple of ways to formulate the symmetric difference operator, either in terms of unions and intersections or in terms of complements. So what we're saying is we want to consider all of the elements less those that are a member of the intersection. So to think of the symmetric difference in terms of the union and intersection operators, we would have asymmetric B equals A union B, and then we want to take away whatever elements are in the intersection of A and B. Another way to think of it is we want to have a look at the union of A difference B and B difference A. Okay, so let's do some work with these operations through some examples.